Good morning. Welcome to Krishna's classroom. Let us continue with our exploration of the abstract integration theory. The problem that we consider today is the following. Suppose x is a measure space. Let Fn be a sequence of extended real value measurable functions. Now the question that you ask here is the following. I mean, I'm not very precise about the statements right now, but we will make things precise. The problem is this. See, we have Fnx. Suppose Fnx converges to f of x for every x belonging to that is point-wise, it converges to a function f. And you can show that f is measurable. If n are measurable, then f is measurable. Okay. Now, our problem is this. Take the integral of dv and take the limit n tending to infinity of this. Is this equal to d? Or in other words, what you are asking for is this. See, integral x f dv is equal to integral x limit n tending to infinity of fn so you are asking the following question. Do the operations of limiting process and integration commute? This is the question. Now we can also put a restriction so that we are conforming to whatever we had been talking about until now. Will make Fn be a sequence of extended of non-negative extended real value functions. Non-negative extended real value measurable. Then Fnx is assumed to converge point-wise to a function f. Okay. So f is measurable. The question is this: can you interchange the integration and the limiting? Okay. Do they commute? Now this is the problem. See, we shall look at an example to see that this is not always true. In general, not true. Let us consider the following example. Take x to be zero, okay? And m the sigma algebra of Lebesgue measurable sets and mu the Lebesgue. The usual Lebesgue measure is what we are measurable space is what we are talking about. X restricted to this. Now we take the following functions. Define Fn to be equal to chi of n plus 1 that means Fn is equal to 1 on the interval n to n plus 1, otherwise it is 0. So one can easily verify that limit n tending to infinity infinity. Or in other words, Fn converges to f which is identically 0 on 0 infinity. Now you immediately see that integral Fn equal to 1. Which is equal to 1. Or it is the length of the interval, or what we call the length of the interval mu of and this is true for every. Therefore, limit n tending to infinity of equal to, it's a constant sequence and this is equal to 1. Whereas integral over f so what do we conclude? Now this shows that this example shows that that in general limit of integral Fn is not equal to integral of now the question is the following. So the question that you ask at this stage is this that's a question. Does equality prevail under conditions of 1? The answer is there are a couple of theorems which gives insight into this, and one can show that it does happen. Okay, but what are the conditions? That is the question. If so, now the monotone convergence theorem is one such result. I hope we have set the background of the problem. Now we are in a position to state the theorem. So we have the background is x at x m mu be a here, of course, we are not assuming any special measure, but something which satisfies all the requirements of a linear measure. Okay. Now we consider the following theorem. So the statement of the theorem. Monotone convergence. So statement of the theorem. Let Fn sequence of extended real valued measurable functions x, and suppose that the first condition is non-negative, we have put equal to also here, so that for some x the function could take the value plus infinity. Okay, so we are talking about extended real value functions, but having this monotonic property. It is a monotonically increasing sequence of functions for every x. That's one condition. The second condition is, of course, this is the most relevant condition. For each x belonging to x, fn x converges to f of x. Now, f of x may take the value infinity for some points on x. Then f is measurable and mu that is limit n tending to infinity of integral x fn mu is equal to integral over x ft. This is the statement of the theorem. Now you see that in the example that we have looked at, you see that this monotone condition is not satisfied. So we mark the functions chi fn form a set of Lebesgue measurable functions on infinity. But is not a monotone class. That is what you have is the condition A is also. So this is the important. So if you have a sequence, so what we assert in this theorem is that if you have a sequence of measurable functions, extended real valued non-negative measurable functions on X with the property that converges to some F, then F is measurable and the integral, the limit of the integrals is equal to integral of the limit. Okay, so that's what we want to. So we now use the proof. Now you look at this sequence. Now this sequence is a monotone sequence of numbers extended real value which are positive, not negative. Therefore, you have now a monotonically increasing sequence of numbers, say alpha n. Then alpha n is monotonically increasing. It may be infinity also. Okay. And you see that alpha n, each alpha n is negative, it's not negative. Okay. Why it is so? This is because integral x So Fn is a monotonically increasing sequence of non-negative extended real valued functions. Then they are measurable, and therefore this inequality holds, that is alpha n is n plus 1. Okay. Then alpha n such that this alpha may be infinite also, may not be finite, need not be finite, it may be infinite. Now the first thing that we observe is, we have proved this before, that Fn is a sequence of measurable functions which converges to f, then f is function. Earlier proved that measurable, and then f is, that is the limit of measurable functions is measurable. Now this we have proved that. So one part is already taken care of. Now we ask the following. Now since Fn is less than or equal to f for every n, we have integral Fn now letting n tends to infinity, then alpha is less than or equal to, so one inequality before. So now what we want to assert is this. So we want to assert that so it remains to prove that is less than or equal to. So that together this would mean that this is equal to. Okay. So let us prove this. This needs little bit of work, unlike the first step. Let S be a simple function, simple measurable function such that is S, the simple function is squeezed between 0 and f, possibly taking the values of at points is taking the values of fx or 0. Okay. C lies between 0 and 1. Now you define En as the set of all x such that now see we keep we shall keep C to be fixed. Okay, right? Since Fn are all measurable functions and S is a simple function, see that En is a measurable set. And also one can show that, you can easily see this, that is even. This is for a fixed C. E1 is contained in E2 etc. And x is equal to. So you have a monotone sequence of sets, each of which is measurable. Okay, such that x becomes the union of this. It's quite easy to check this property because here you are using the property that Fn is less than or equal to Fn plus 1. So monotonicity is used. Okay, and then you see that this is the bound, and see, you have f is approximated from below by a simple function or something below that. Okay, then you take c times below that, c times sx, so you have a function like. Okay, so let me draw some picture. Yeah, suppose this is your x. Okay, and you have a function. This is your f. Okay, now you have some sx, and c times sx is going to be some function like this. It's below that, certainly below that. Okay, and elsewhere it is 0, 0 here, 0 over here, 0 over here, 0 over here, then is 0 over here, and so on. So it's a simple function. This graph is given. C times, let us assume that this is C times, and Sx itself is less than Fx, therefore C times Sx is less than or even less than or equal to. Now you look at this set, the set of points x for which fn x is greater than or equal to x. Okay, so fn x is, some places it may not be, okay, and some places it may be above this. Okay, so we are taking those x for which fn x is greater than or equal to c times 6. Okay, now you see that fn plus 1 is greater than or equal to fn. Okay, therefore you see that wherever every element of en plus 1 satisfies the condition that x fn plus 1x is greater than or equal to c times sx, and you see that fn x is okay, so what we have is fn so you have c times sx is less than or equal to fn x is less than or equal to fn plus 1x automatically. So you see that en plus 1 is, en is contained in en plus 1. Okay, so that's easy to see. Just write down the inequality. And then also you can show that every element of x is in one of the ens. Now, in fact, it's a telescopic sequence that you have. Okay, so you see that because of this condition and this, you see that x is equal to union n. We'll just prove this for, let x belong to x. So let x belong to x. If fx is 0, then what you have? E1. Okay. So f1x is greater than or equal to c times sx, and you see that this itself is 0. Therefore, this is Fn is positive. So, it is just the condition that F1x is greater than or equal to 0. Okay. If f of x is greater than 0, then c times sx is less than f of x. Since c is less than 1, because sx is less than or equal to fx, c is less than 1, therefore this is true. So we have found if x is a point where fx is 0, then it is in even. If x is a point where fx is greater than 0, then it is going to be some en or somewhere. Okay, what does this mean? This means okay, or but the other inequality is clear because every element here is certainly in x. Okay, or we have by the definition of en, that we have to. That's quite easy. Now we look at this integral. So we see that integral over x fn d mu is greater than or equal to, because en is contained in x, you have, and fn's are non-negative, en and this of course is greater than or equal to c times integral over en look at the definition of en. Okay, c times sx is greater than or equal to fn. So we are using that. Sorry, fn is greater than or equal. So c times sx is less than or equal to fn. Therefore, see, because of this inequality, you see that this is okay. So this from the definition of that is true for n equal to 1 to infinity. Now in this inequality we let n tend to infinity. Now in this we let now what happens is En is a telescopic sequence, okay, which increases to x. Okay. So now let us work out this one. Now this is what we are trying to work out. Okay. So we have limit what happens, what about this? We have seen that measurable set such that An and then mu, the measure, any measure, mu of An converges to mu of okay. Then we have also seen that for any measurable step function, measurable simple function, S 6 integral over E any measurable set, B mu is equal to some phi of E, where phi is an then we have, because we have this result, phi of En we have a sequence. Now x is equal to union En and En is contained in En plus 1. Then what happens? You have limit n tending to infinity of phi En equal to phi of okay. And what is phi of x? Phi of x is essentially the limit of yes. Okay. So this we have, this result we have. So we use this result here. This is all because the phi that you define here is a measure, and for any measure, this condition is satisfied, and therefore we get this result. Okay. Now let us work with this. Hence, by letting n tend to infinity, n tend to infinity in this one. As we have we have integral over x, or this is alpha. Alpha is greater than or equal to c times, and limit of this one is essentially integral over x. So this, from this to this, you are justified because of this property. That's important. That's one of the results that we proved earlier. Okay. Now this result holds for all c such that okay, therefore, which implies alpha is there is S. Okay, and this is true for every simple function. Yes, it's that. And that gives the, see, the supremum of this taken over all the S would give you integral of F. That is, alpha is greater than or equal to, take the supremum of over all S. This is equal to integral over x f. Get the definition of this. Okay. Therefore, we had one earlier inequality. The earlier inequality was alpha is less than, together with we immediately have the results, namely we have alpha equal to, what is this? That is, what is alpha? Limit n tending to infinity of integral fn d mu is equal to now this is what we want. Therefore, under the monotonicity assumption, we get equality in the limit. Okay, and we have also seen that this is something which we cannot, or this condition or some other condition. Okay. What we say is that a sufficient condition for the commutativity of the integral and the limiting process happens is that Fn is a monotonically increasing sequence. That is the content of the monotone convergence theorem. Now we look at a simple consequence of this. In fact, this can be thought of as a corollary. If sequence that means it is an extended non-negative real valued measurable function. Each Fn is this. So, is measurable etc. And f of x equal to now you should realize that each Fn is an extended real valued function, and therefore this sum may be infinite. Then what we have is integral over x f d mu is equal to sigma n equal to okay, that means the summation and integration can be interchanged. Okay, so this I'll just look at this part before we prove this. Okay, what will be the strategy of the okay? This means the last line we will interpret. Okay, so this is actually this is equal to this. But what we have is for finite sum, see this is actually uh, as n tends to infinity. Now what we are proving is this. Now you see, look at this sequence. So let then each Gn is measurable. And you also have Fn, each Fn is non-negative, means Gn is, that is Gn is measurable and monotone. Therefore, we can apply the above theorem. Okay, what does it say? So limit n tending to infinity of Gn is going to be this is equal to, you can interchange these two because it's finite sum that you have. One to n. Now what we want to prove is that this is equal to now this is the sort of argument that we want to build. Okay. So what we have is this side is actually limit n tending to infinity, capital N tending to infinity of sigma k equal to 1 to n, that is limit is equal to that means this limiting process and the integration can be changed. So it's the commutativity of the limiting process with the integration. Now this is the strategy of the proof. Now let us prove this theorem. We write a recursive. P sequence of simple measurable functions such that one and now if SI double prime, then you see that these are two simple functions and their sum is also a simple function. Okay. F2. Now by the monotone convergence theorem combined with, so what we have is this integral over x s plus t, this you recall, d mu equal to integral over x s d mu plus integral over x t d mu. This we have proved already for simple functions. That means this is a measure. These are two measures phi and psi. Now this is what we towards the end of the last lecture. If this is a measure phi, this is a measure psi, then phi plus psi is a measure. Okay, so phi plus psi is equal to phi plus psi. Phi plus psi of x equal to phi x plus psi x. Now this is what we have. Now we use this result. Okay, so let us recall this result. Consequently, you have integral over x f1 plus f2 d mu. This is equal to, you see, this is, you have the supremum through s prime and s double prime. So you get this result as integral over x. Now extending this result further, we use the idea that we have discussed already. Okay. Put so finite sum. So you can extend this result finite sum. Okay. Then what you have is integral over Gn so you take these functions, apply monotone convergence theorem. Dn. Then you obtain infinity that is because Gn is what you have, and apply monotone convergence theorem to frequency. Okay, so that completes the proof of the monotone convergence theorem and a useful or one of the ways in which we really apply this result. So, thank you very much.